One of the intuitive questions we might have at this point is, well, when does this apply? When are we going to need this? So we're going to take a look at the example of a spring mass system. Spring mass systems are often described in physics as you have some sort of wall or stationary point, and you have some mass attached to it. So it could be a weight of some sort. And between that weight and that that fixed stationary wall or ceiling, there's a spring. And if we all know that if you were to pull this side out to the right here and release it, that spring would want to bounce back and forth until it sort of slows down, fights the forces of friction, and comes to a rest. The other examples are buildings and earthquakes. So if you think about a building and you think about what happens when that building it encounters an earthquake down here, this thing is going to kind of sway from side to side a little bit, right? It's going to kind of do this and sway over here. It's going to sway back and forth to try to stabilize itself out. Also, whenever you think about a strut or shock assembly, shock and strut assembly in your vehicle, you know, your vehicle, and this is going to be a very, very poor rendition of a car, but in your wheel well, right, you have your tire attached down here, and your car is, of course, resting on that, and every time you go over a speed bump or something, you can feel that you have something in there that's sort of breaking that fall, so it doesn't feel like you hit a big lump. So anything that has suspension, also electrical circuits, behave like spring mass systems, although we won't go into that here. So this basic model, even though it seems like a contrived physics problem, is really important in describing a lot of types of motion. So here we're going to have a mass. This is going to be m, and it's often measured in kilograms. Okay, it doesn't have to be measured in kilograms, but we like to stick with metric units. B is, well, let's look at K first. K is what we call the spring constant. And every spring has a spring constant. And we'll describe what the spring constant actually does in a moment here, but it kind of describes how stiff or how stiff the spring is. So a stiffer spring, like one in the car, is going to be valued at a higher K than, say, like the spring in your mechanical pencil. That's going to be a very low value of K. Now this thing is going to be measured in newtons per meter. So basically it's the amount of force that is applied for every meter of displacement, and that is assumed to be constant. And so then we also have this thing called B, and you might be wondering what this is. Well, oftentimes this is referred to as a dash pot, and this is what we call the damping coefficient. So in the spring, there's actually something called a strut that kind of comes down through here, and it uses pneumatic pressure so that even though the spring will continue oscillating, but this, what it does is it resists the oscillation and it kind of slows them down. So, for example, if you've ever seen a door in like a mall or a store, that door never slams shut. In fact, if you look at the top of the door, there's usually some sort of hinge that has some tube-like structure. This thing here is often referred to as a dash pot. So as this thing moves back and forth, the two ends of this little guy kind of create friction and slow this down. It's kind of a weird illustration, but anything that's going to slow down the oscillations. And this is going to be measured in newtons per meter per second. So basically this is the amount of force that this damping coefficient applies for every unit of velocity. Something that you'd get into more in a physics context. Okay, so furthermore, suppose there's something that dampens the oscillation of the back and forth movement. We will call that a damper. So if we stretch the mass, for example, we expect the release of such a mass to result in slowly diminishing movement until finally the mass comes to rest. So we should kind of expect this to slowly stop oscillating because there's enough friction here that is sort of overtaking the force of that spring. So let's build this model. This model starts off with Newton's second law, which basically says the the net force is equal to mass times acceleration. So all forces are additive, meaning we sum the forces to get the net force. Okay, so what kinds of forces do we have in here? Well, we have the force of the spring. And there's something known as Hooke's law that describes how this happens. This is taken from physics. And as mathematicians, we probably don't need to worry too much about it. We just need to know that this is something that physicists have studied. So the force sub spring, that's just allows us to see that that's just due to the spring itself, is negatively proportional to the displacement. Now this should make sense if you've ever stretched a spring, and let's just say here you have your spring, and here is its rest point. Here's where it would want to be if you didn't do anything to it. So if you just let it sit, it would sit in its normal position. Now imagine that you stretch this thing out, and you continue stretching it out this way. Where does that spring want to go? Well, the spring wants to go back to rest, right? So the force is this direction, and the more you stretch it out, the stronger that force is in that direction, which explains why the spring force is negatively proportional to the displacement. So if we define y equals 0, y is the displacement from rest. From rest point. So if you put no compression or stretch on that spring itself, it would want to stay coiled up right here and stay stable at y equals 0. Now we're going to define any movement going this way to be y greater than 0. That's going to be a stretch. And we're going to define y less than 0. So if you go this way, we're going to define that to be a compression. Now, so if you compress the spring, it wants to go the opposite direction. And the more you compress it, the stronger that force is in the opposite direction, which is really all Hooke's law is saying. Now, all forces that resist movement of the spring are bucketed into the damping force. So we'll say the damping force, what it does is it opposes velocity. So for example, if that spring is moving this way, the damping force will proportionally slow it down, right? So it's still going to allow that spring to move this way, but it's going to start to slow it down until it goes back, and it's going to slow it down, and it's going to slow it down until eventually that spring kind of stops moving and it stays fairly stationary. The final force that we'll consider is that of what we call forcing functions. Now, forcing functions are forces that are not inherently part of the spring mass system. For instance, the force of gravity, that has nothing to do with the spring mass system itself. That is an external force. And from physics, what we know is that the force of gravity is the mass multiplied by the gravitational constant. I think it's negative 9.8 if you're dealing with the metric system. And that's just going to be written as m times g. So the forcing force, we just call that F sub force, is equal to mg. Now, according to Newton's second law, if we want to sum all these forces, so force equals, there's the spring force, there's the damping force, there's the gravitational force, that's what replaces F, and that's equal to mass times acceleration. Now, where does the second derivative come in? Well, acceleration, A, that's the second derivative of displacement from rest with respect to time. Therefore, we could replace A with the second derivative. And that leaves us with the sum of the three forces equals mass times acceleration, which after rearranging, typically we want all the functions of y on the left and everything else on the right. So if you add b dy dt to m times acceleration, if you add ky to that, then you get something that looks like this. Now, the mass value is in front of the acceleration terms, but if we divide both sides by it, then the damping force gets divided by m, the spring constant gets divided by m, and I guess technically so does this over here. Now, with that said, this forms what we call a non-homogeneous second-order linear differential equation. So it's non-homogeneous if the left-hand side, if the right-hand side. So if this right-hand side was 0, as you see, all the y terms have been, anything involving y has been moved to the left. If what you have on the right is not 0, then it's non-homogeneous, just like with first-order equations. If this does end up being 0, for example, let's say you're ignoring the effects of gravity, or gravity is not really coming into play because of the way the spring mass system is positioned, then this could end up being 0. There's no external forces beyond that of the system itself. If you remove this mg, it would become a homogeneous. So if this were 0, or if you were in a gravity-free zone or a vacuum of some sort. Now, if you kind of look at this thing and you write the second derivative as y double prime, you can see that these are constant coefficients right now. The damping force, the mass, and the spring constant are all fixed in that situation. They're not functions of time. But in general, if we go beyond just the spring mass system, we may want to study situations in which this coefficient is not a constant, but it's some function of time. So we're just sort of broadcasting forward. We're foreshadowing what's to come later. Same thing here. This in general doesn't have to be a constant. It could be some function of time. And that this over here can also be some function of time. And so this would embody the non-homogeneous second-order linear differential equation that we want to study.